Okay, so this is problem 4100. All right, I have shown the problem up there on the upper right hand side of the screen. And what this problem is actually asking for is for us to find the equivalent force and moment at B. Okay, so the problem is asking if we have all those forces, the 2.5 kilonewtons, the 1.5 kilonewtons, and the 3 kilonewton force. If we wanted to create a specific type of loading by stripping all of those forces off, and over here is point B, right? What force, resultant force, would we put here, as well as what moment? So the resultant moment there. So, and create the exact same loading scenario as what's shown in the diagram. So let's do our analysis. All right. So let's first tackle the equivalent force, the resultant force. And to figure this out, we need to take the sum of the forces. All right. And the sum of the forces will equal the resultant force. Now, in our case, we probably need to break this down into x and y components. So let's start out with the x component equals the resultant force in the x direction. So starting with the 2.5 kilonewtons, and we're calling, x is positive to the right and y is positive up. Okay, so we have the 2.5 kilonewton force. So that is the component in the x direction is actually negative, so negative 2.5. And as we see, the horizontal component there is 4 and the hypotenuse is 5. So that would give us the component in the x direction. All right, and moving on to the 1.5 kilonewtons. So 1.5, but we need the component of that. And that looks like it's going to be the sine of 30 degrees. And lastly, the 3 kilonewton force is going to have no impact in the x direction. So that is just the force resultant in the x. And by performing that calculation, we come out with a number which is negative 1.25 kilonewtons in the x direction. All right, now let's do the y direction. So the sum of the forces in the y is going to equal the resultant force in the y direction. And starting with the 2.5 kilonewtons, that's pointed in the negative direction. The vertical component would be in the negative direction. So we have negative 2.5. And the vertical is 3, hypotenuse is 5 still. All right. And the 1.5 is also going to be negative. So we have 1.5. And this time it will be cosine of 30. And lastly, we have the 3 kilonewton force, which is pointed directly downwards. So that comes out to be negative 5 point, I'm going to leave a few more decimals on here, 5.799 kilonewtons. Negative. All right. So to figure out the resultant force now, these are components. So what we have in the x direction is 1.25 kilonewtons this direction. And we have downward, we have 5.799, right? And our resultant vector, FR, is going to be in this direction. So we can call this angle theta here. So doing the Pythagorean theorem, we have 1.25 squared plus 5.799 squared is going to equal the magnitude of FR squared. And FR comes out to be, the magnitude of FR comes out to be 5.93 newtons. Oh, kilonewtons. Okay. And what angle does that act at? So we need to figure out theta as well, because we have the magnitude, we just don't have the angle that it acts. So to do that, we can use the tangent. So tangent of theta, remember that's opposite over adjacent. So we have 5.799 divided by 1.25. Once we figure this out, we can take the inverse tangent here to figure out theta. So theta is equal to 77.8 degrees. Okay. So our resultant vector is equal to 5.93 kilonewtons at an angle downward of 77.8 degrees. So that's one part of the problem. We figured out the equivalent force at point B, but now we also need to figure out the resultant moment at B. So to do this, we would say we need to figure out the moment at B. And we'll call counterclockwise positive like we normally do. And so let's start with the 2.5 kilonewton force. So we have 2.5, right? But it's not the full 2.5. We have to take the component, right? Which is just the downward component of that force there. So we have 3 over 5, right, being the downward component of that force. And the distance it acts away from B, so the distance from B to where that force is applied is 2 plus 4. So that becomes 6, right? And we need to make sure that it's in the right direction. So that force, that downward force would create a, let's go back up, let's take a look. If the force is here and it's downward, right there, it would create a counterclockwise motion around B. So we are correct in stating that that should actually be a positive value there. So coming back down, we have the positive or negative correct on that. All right, and so we're moving on to the 1.5 kilonewton force, and that's, we only want the downward component of that, and that's also going to create a counterclockwise motion around point B. So we have 1.5, and the vertical component of 1.5 should be cosine of 30 degrees. Okay, and then we need to multiply that by the distance it is away from B, which is just 2. And lastly, we have the 3 kilonewton force, and that is directly passing through B. So that will not create any rotation or intended rotation around point B, so we can keep that off of there. So we have everything here, so that is, we do that multiplication, that's 11.6 kilonewton meters, right? So the moment that we would replace place around B for the equivalent moment is 11.6 kilonewton meters, and that is counterclockwise. So that's the second part. So just reviewing, if we were to take all of these forces off of this beam and wanting to replace it with a single force in a single moment, these would be the two forces. We replace this force at B and this moment at B, and it would create the exact same loading condition.